Hello, this is Jonathan Templin, and this is a lecture about simple marginal and interaction effects in general linear models. To look through this lecture, I have slides that are available on my website, the interactions set of slides. I've also downloaded the R syntax that will run the example for us. So let's begin. In today's lecture, we're going to talk about centering and coding of predictor variables in a linear model, talk about interpreting parameters in the model for the means, what to do with main effects when we have interactions, and a little bit about a regression versus ANOVA, although this difference is not as big as it seems when you look at in R as it would be if you looked in other statistical packages. So to begin, let's look at today's example. Let's imagine we have a study examining the effect of a new instruction method on test performance in college freshmen versus seniors. So the dependent variable would be a test score. And what we're going to do is to dummy code the status of a person, whether a person was in the new or the old performance. So there'll be a variable named new, where a person in the new group will have a 1, and otherwise a person in the old group would have a 0. And we'll have a variable named senior, which represents a person who's a senior in college versus with a 1, and a 0 would be a freshman in college. And there'll be 25 people per group. That's less relevant at the moment. So the linear model that we're going to do, since we have two-level categorical predictor variables. This is essentially what we would call a 2-by-2 design, a cross design. So we would have basically 25 freshmen in the old method, 25 seniors in the old teaching method, 25 freshmen in the new teaching method, and 25 seniors in the new teaching method. So we have a completely cross design. We have people in each of the cells of this 2-by-2 table that you see below here. And the linear model that we're going to build to evaluate the impact of whether or not the new method does better than the old method, or whether or not seniors do better than freshmen, is this right here that you see. We're going to take the test score for a person, so test sub P, the P stands for person. It's going to be equal to an overall intercept, plus the main effect times of senior, main effect of the new method, and then an interaction term between senior and new. And then finally, there'll be an error term, and the error term will follow a normal distribution, the mean of 0 and a variance of sigma squared. Now, in the table that you see below, you can see the means for each of these groups, broken down by group and by margin. So, for instance, freshmen in the old method scored on average 80, seniors in the old method scored on average 82. Freshmen in the new method scored on average 87.96. Seniors in the new method scored on average 87.08. And the numbers that you see below that represent the standard deviation and the standard error of the mean. Now, on the right-hand side is the marginal mean, meaning if we aggregate across freshmen and seniors, we can get the mean for the old method of teaching of 81.28 versus the new method of teaching, which is 87.52. And the bottom, again, you'll see the marginal mean. This time, 84.08 is the marginal mean of all freshmen, and 84.72 is the marginal mean of all seniors. And then finally, the overall grand mean. This is the thing that marginalizing across both freshmen, seniors, and then old and new method. This is an overall average test score of 84.40. So we're going to first start with centering and coding predictors. And we're going to focus today, again, this is the overall picture of a linear model that we have up here is we have a dependent variable. It's equal to some set of predictors multiplied by some beta coefficients or regression slopes, what we will come to call fixed effects later on in class. This is also the model for the means, as it provides the predicted value or the mean prediction, the predicted value of the mean for a person with a given x and a given z. As opposed to the error term, which is really the model for the variance. And in a linear model, there's not much of a model for variance there. There's just one parameter. It's sigma squared error. So once again, the model for the means gives each person's expected or predicted outcome, conditional on a given x and a given c. So you know an x, you know a z, you plug each of those into this formula, right, this part of the formula in the orange, and you get a mean prediction. So here we have 4 fixed effects that show up in the model for the means in this example. And then over in the model for the variance, this talks about how much variability there happens to be on average across in each of the across each of the conditional values. And we have only one parameter. It's sigma squared error. It's the residual variance. We saw before the residual variance is useful for describing how much variation is left once you account for the means themselves, and it helps us describe our overall R squared, a proportion of variance accounted for in a model. So move on to the fixed effects. So from now on, what we need to do is to think carefully about how the predicted variables are entered to the model for the means, because what we do with the values of the predictor variables has an impact on some of the fixed effects or beta coefficients. And we're going to see that pretty quickly when we move in, but the very first place that we see that is the intercept. So now, about the intercept, most people don't often care what the intercept happens to be because it goes without interpretation. It's effectively kind of a parameter that shows up just by default. It's sort of the average. What the intercept represents is the predicted value of a response when all of the predictors are equal to 0. So that is something that people don't usually care about, and so we'll see later on, once we get into more complicated models, yes, it does matter occasionally where the intercept happens to be. But beyond that, centering predictors and centering centering the predictors, excuse me, does not affect much about the model with the exception of the interpretation. So it does not affect the total amount of outcome variance accounted for. It does not affect your R squared. So you center a predictor, you don't center a predictor, you get the same amount of R squared. That's one of the reasons people don't care. It does not affect the outcome values predicted by the model either. So if you center a predictor, the other model parameters readjust to where they need to be with the centered predictor versus the non-centered predictor, and sure enough, when you go make a predicted outcome, when you plug in your predictor and you multiply it by the beta coefficients, you still get the same predicted response, whether it's centered or not centered. So that's another reason why people don't typically care about centering. But why centering does matter to us is because for certain parameters, and specifically the intercept, always, and main effects in the presence of interactions, the values of those parameters, the values of those beta coefficients, depend on where 0 happens to be for the predictors. So if you're trying to provide an explanation of what's happening based on the parameters of your model, knowing where 0 is makes a big difference. So for the intercept, it's fairly evident because the intercept is the expected outcome value when x equals 0. And for instance, if we have a linear model where we have height in the model, the intercept at height equals 0, like say height in inches, height equals 0 would be a nonsensical value because we have nobody of height 0. That person would not exist. So the intercept itself is again less important, but what we need to do is worry about more importantly are the interaction effects as we go forward, because the interactions really do depend on where the intercept happens to be, and we're going to see that very shortly in this example. So for continuous predictors, what we can do is to make the intercept interpretable by centering. So if we have a continuous predictor, something like height or weight, what we can do is subtract a constant from the intercept, and now the new predictor will be centered. So for instance, a typical thing to do is take the mean of the predictor. So let's imagine we have height in a sample of people. The height maybe 67 inches. If we want to center height, we take each person's height and subtract off the mean of 67 inches. And now that centered variable is what we enter into the model. And then the intercept is then the expected outcome, not for height equals 0, but it's now for height when the centered variable equals 0. And the centered variable equals 0 when a person's height is equal to the mean height. So centering shifts the intercept over slightly. Another way of doing so, sometimes people think of as better, is to center around a meaningful constant. So the mean is just a number. It's just a constant. Another thing to do would be to think about a meaningful height. So maybe, for instance, you're in a population of fairly tall people. Perhaps you want to center around 72 inches tall, which is the 6-foot mark. Then you can talk about height. Then the intercept would represent the predicted outcome for a 6-foot tall person. You could pick anything that you pick, though, is arbitrary because it's everything gives you the same result. It's just understanding what the numbers mean as a consequence of where you put the predictor itself. So that's for continuous predictors. But for categorical predictors, what we have to do is we have to code them. And by coding them, we effectively establish what 0 happens to mean. Either we code them ourselves by specifically transforming our data to be a 0 and a 1 if we have a 2-category group, or we allow a program like R to create a coding system for us. And the 0 value is given to a group that we often call the reference group. The reason why we call this the reference group is because if we have a single variable linear model, and let's say we have men and women, so we code women with a 1, men with a 0, then the mean or the intercept represents, again, the predicted value when all the predictors are 0. So the predicted value would be the mean for men, or the mean for the reference group. So we're given the title reference group because that intercept is the mean of that group itself, and all the other parameters are then in reference to that group's mean. So we're going to see this much more in our example as we go forward today. So we often call this reference group coding or dummy group coding, and you can see this 2-group example below here on the slide. For more than 2 groups, what we need to do is create a system of dummy codes or a system of coded variables. And what we'll have is, if we have a total of, for a given number of groups, if we have capital G groups, say, then we need G-1 new variables to come into an analysis. And so, for example, let's imagine we have four groups: control, treatment 1, treatment 2, and treatment 3. With 4 groups, we will need 3 dummy coded variables. And again, we have to pick, or the software picks for us, what the reference group happens to be. In this case, the reference group is the variable where everything happens to be 0 across all the 3 variables. So dummy code 1, right here, where we put a 1 for treatment 1, so everybody in treatment 1 gets a 1, everybody else gets a 0, will then represent the difference between the control group. So the beta coefficient that multiplies this dependent variable, or this independent variable, will represent the difference between the control group and the treatment 1 group. And just to go back to this, once we establish that control is our reference group, again, the intercept represents the mean of the control group. So this beta coefficient for dummy code 1 represents the difference between control and dummy code 1. The second dummy coded variable will give a 1 where a person is in treatment group 2, and a 0 otherwise. And that would then represent the difference between control and treatment group 2. And likewise, for the third dummy-coded variable, we'll get a 1 for if a person's in treatment group 3 and a 0 otherwise. And this will represent the difference between the control group and treatment group 3. Now, when you do this, again, it's arbitrary. You could pick control, you could pick treatment 1, 2, 3. What is most important, though, is to understand which group is the reference group, because that will have ramifications, particularly when you have interaction variables in the analysis. And certainly it has ramifications for understanding what the meaning of each of the beta coefficients for D1, D2, and D3 represent. some of the things that you have to think about when you're doing this. If you're dummy coding your variables yourself, then all predictors representing the same group must be in the model at the same time. So once again, if we had these 4 variables, 4 groups, we'd need 3 predictor variables. If we left one or more of these out, the analysis would not be complete. We would not be able to describe the difference between whatever variable, the group represented by whatever variable we left out, and the control. So it won't tell the full story. Now there are other different types of coding that people can do, and there's actually, we could spend almost a half a semester describing the different types of codings that people can do for dummy codes, for group variables. This falls under the heading of contrasts. One version of that, one very simple version of that, is something we call effect coding. If we were to give a negative 0.5 to men and a 0.5 to women, then the intercept would not necessarily represent anybody, but what the intercept would give us would be the grand mean of the group overall. In software, this rarely is a default, although you can do this. And depending on the type of analysis situation you are in, you may have a need to do this, although I've found in practice it's very infrequent, because basically anything that you need to do with coding you can redo later on with the beta parameters as we go forward, and I'm going to show you that just a little bit with the R syntax. So, going back to that 4-group example, here's a model. We have an outcome y, we have an intercept beta 0, we have beta 1 times the first dummy-coded variable, beta 2 times the second dummy-coded variable, and beta 3 times the third dummy-coded variable. And we have error with your typical residual variance. So let's interpret these parameters real quick. Intercept represents the predicted value when all the predictors are equal to 0. We know D1 is 0, D2 is 0 for anybody who's not in treatment group 1. D2 is 0 for anybody who's not in treatment group 2. And D3 is 0 for anybody who's not in treatment group 3. And so in combination, we know all 3 are 0 simultaneously for somebody in the control group. So beta 0 represents the mean value of the control group. So beta 1 then represents the difference between the mean of the control group and the mean of treatment group 1. Beta 2 represents the difference of the mean of the control group and treatment group 2. And beta 3 represents the mean of the difference between the mean of control group and treatment group 3. So all 3 show up there. But similarly, if we wanted to just come up with what the means happen to be, we'd have to go and plug the betas back together. So here in the control group, beta 0 is the mean for the control group. The treatment 1 group mean, the way we could find that is by plugging in the dummy codes for someone who is in treatment group 1. So here are our dummy codes. In treatment group 1, that's this column right here. Treatment group 1 provides a 1 right here for D1, and the zeros for D2 and D3. So when we put a 1, when we zero out all the other parameters, this part right here is 0, zero those out, we are left with beta 0 plus beta 1. So what we see is the treatment group 1 mean is beta 0 plus beta 1. Likewise, we could do the same thing with treatment group 2 and treatment group 3. We would plug in the dummy code for a person in treatment group 2. We would see that beta 0 and plus beta 2 are the only things left in the model, and we'd say that is the mean or the predicted value for a person in treatment group 2. And similarly, we could do the same thing for treatment group 3. So the model for these 4 groups will directly provide, in the form of beta 1, beta 2, and beta 3, directly provides the difference between each group mean and the reference mean, the control group. But indirectly, it provides the mean of every group through these beta coefficients. And if we know the mean of each group, we could come up with a mean comparison that's not at all in any of these models. So for instance, what if we wanted to find the difference between treatment 2's mean and treatment 3's mean? Well, if we wanted to do that, we could pretty quickly by taking the following. We know that beta 0 plus beta 2 happen to be the mean for group 2, treatment group 2. And we also know, if we want to take the difference, we know the mean for treatment group 3 is beta 0 plus beta 3. And so if we do a little bit of factoring, we see that the beta zeros cancel because there's a positive beta 0 here and a negative beta 0 here. And we see that the difference between treatment group 2 and treatment group 3 is then beta 2 minus beta 3. So the difference between treatment group 2 and treatment group 3, beta 2 minus beta 3. Effectively, we could do anything like that with any of the mean comparisons we're interested in. All we need to know are the betas that come out of the model itself. So here we go. Here are all the different types of dummy codes that we could do, all the different comparisons we could do, and how we would go and figure this out. And this is the key to making sense of a linear model, making sense of all the different comparisons you might want to get into. So it's just a little bit overwhelming when you think about it. We have 4 different variables here that provide 6 group differences. Some of those are direct, beta 1 and beta 2 and beta 3. And some of those are indirect. We have to take the difference between the two. Now, in R, there is a package that helps with this. It is the Multicomp package right here. This is a multiple comparison package, and what it allows you to do is to capture the betas of a linear model, and then to create the differences that you want to see. It will then go grab the numbers for you, produce the mean differences, but more importantly, it will produce what shows up in R that you can't necessarily easily compute by hand, is the standard error of the mean difference. So if I go back one slide, we have here a bunch of mean differences, beta 2 minus beta 1. So this is, let's imagine we see here the treatment group versus treatment 1 versus treatment 2. We know the mean difference is beta 2 minus beta 1, but what if we wanted to provide a hypothesis test for that? Is that significantly different than 0? How would we tell? An easy way to do so is to take that mean difference and divide it by its standard error. But calculating the standard error is not possible just by taking the mean differences. To calculate a standard error, you need to know not only the standard errors of both of the coefficients, beta 2 and beta 1, but you also need to know the covariance of the coefficients as well, and that's something that's buried deep within output or deep inside an object in R. Well, the GLHT package makes that easy, relatively easy for you. It makes it obtainable for you. I think everything is with R is a relative ease. I don't know that anything in R is easy. We go into this. How this package works is the following, and we're going to have lots of practice on this as we go forward, but let's imagine we have this linear model here, y being predicted by D1, D2, and D3. So we'll have these 4 beta coefficients, beta 0, beta 1, beta 2, and beta 3. If we wanted to calculate the mean for each of these, we have to form what's called a matrix in R, a new type of variable. And the matrix itself will have elements of for a specific value or specific numbers for each of the 4 beta coefficients. So this you can think of them in order. This is the first spot of this sequence of 4 numbers represents the beta 0 coefficient. So when we put a 1 there, it's like taking beta 0 times 1. So we want just that. What's going to be formed from this is each of these coefficients is going to each of these numbers in this sequence right here is going to multiply its respective beta coefficients. So in this little snippet that you see here, we have 1 times beta 0, 0 times beta 1, 0 times beta 2, and 0 times beta 3. So those numbers multiply the beta coefficients, and then we sum together that multiple at the end, and that result is the thing that we want to have. So 1 times beta 0 plus 0 times the rest gives us just beta 0, This term over on the right-hand side after the semicolon tells us that we're going to label this the control group mean. And we could do the same thing for each of the other means of our groups. So beta 0 times 1 plus beta 1 times 1 gives us the mean of treatment group 1. Beta 0 times 1 plus beta 2 times 1 gives us the mean of treatment group 2. And beta 0 times 1 plus beta 3 times 1 gives us the mean of treatment group 3. And now, once we have these means formed, we could go and take each of the 6 contrasts by just taking the difference between mean 2 and mean, using a subtraction with each of the mean variables or objects that we've saved previously. So contrast 1, this would be the difference between control group and treatment group 1. Now we know this comes directly out of the model, but this is for completeness sake. Mean 2, we just take mean 2, which is treatment 1 mean, minus mean 1. And sure enough, that gives us the value, or that starts to load up the process. We can do this for all 6 combinations. If we glue them together, calling this is a function called rbind, which takes each of the rows of these matrices and puts them all into one big matrix. Then at the end, we submit that to GLHT, this GLHT function, General Linear Hypothesis Test. That will give us, the summary statement will give us the mean difference for each of those contrasts. It will also give us the standard error of the mean difference and a p-value for each to see if it's significantly different from 0. And there's all sorts of options that you can do with that. In analysis of variance, we are often concerned with multiple comparisons. So we have now 6 contrasts. We may have to adjust the significance level or adjust the test itself to make sure that we don't have an inflated type 1 error rate, for instance. And that can be done as well in the package. But I'll show you a more concrete example as we get later in the lecture. So if we look at the intercept itself, the intercept means to you is effectively a you are here sign, right? It's kind of where you start to understand where you're going in your analysis. So as we go forward, we are going to start there. But let's talk a little bit about main effects within interactions. So interactions. The literal makeup of an interaction is one predictor variable multiplying another. And that product then is a predictor in and of itself of a dependent variable. So the term interaction really talks about, is also synonymous with the term moderation. Moderation really comes from the idea where that this interaction modifies or moderates the main effects of the variables that go into it. Meaning, when you have an interaction present, if you have this interaction between x and z, this interaction serves to change the effect of the x or z by themselves. So it moderates or it modifies the main effects of the model itself. Interactions can always be evaluated for any combination of categorical and continuous predictors, although traditionally in ANOVA, if you're doing default in most software like SPSS or SAS, if you do an ANOVA function or an ANOVA part of the model, it will include the interactions for you automatically. If you add in a continuous predictor to your ANOVA, it will not necessarily, not automatically provide the interaction of the continuous predictor with the categorical predictors. And then somewhere, if you're doing just linear regression, it doesn't often give you any type of interactions whatsoever. So it's this odd history of interactions with respect to software. In practice, though, interactions are one of the most powerful effects that you can formulate within science, and the understanding of how to interpret interactions means a lot for discipline-specific fields, because what interactions start to do is they tell you when certain predictors are significant, because perhaps x only matters only over certain ranges of z, or Z only matters for certain conditions of X. So what interactions will do is sort to tell a more fuller story of what's happening in an analysis itself. So main effects of predictors within interactions in GLM. Main effects within interactions should remain in the model regardless of whether or not they're significant. So what do I mean by that? If you go back to the slide right here, if you plug in this model right here, and you find beta 3 is significant, but beta 1 and or beta 2 are not, there may be a thought to take both of those out of the model. Don't. Every term that shows up in the interaction, for every variable in the interaction, the lower order effects must be in the analysis itself, and that's because they are there to serve as control conditions. Moreover, what you're going to find is this interaction is an over-additive or under-additive effect. So it needs to be added to something, and that something it's added to are those main effects that show up below it. So the role of the two-way interaction is to adjust the main effects. However, the concept of main effect, as we knew it from before, directly no longer applies. Each main effect is now said to be conditional on the value of the predictor that it interacts with. So what do I mean by that? Let's go back to this model statement here. In the presence of this X by Z interaction, X, or the main effect of X, beta 1, is the main effect of X when Z equals 0. And that's because if Z were to equal something else, once we put that number in, there would still be X right here multiplying a constant. We would have to add to that main effect to describe the story of it. So main effects are now called conditional main effects, or sometimes called simple main effects. So for an example, let's imagine we have a model where we have Y being predicted by a main effect of X. Excuse me, that's a W. A main effect of W, a main effect of X, a main effect of Z, and the interaction of X and Z. So you'll see now that the effect of W, because there's no interacting variable multiplying W, the effect of W is a marginal main effect, or it's just a main effect as we'd call it, because it's not part of an interaction later on. However, the main effect of X is now a conditional main effect because it is part of the X by Z interaction. So that main effect, that beta weight that's multiplying X, is interpreted as the beta weight when Z equals 0. Similarly, the effect of Z is now the conditional main effect of Z, and it's interpreted specifically when X equals 0. So why centering became the first part of this lecture is because centering, or knowing where 0 happens to be, is necessary to figure out what the effect stands for, what the main effect or conditional main effect stands for when an interaction is present. So let's take an example here. Let's imagine we have a grade point average for a person, and we're going to predict it by several variables here. We have an intercept, we have a main effect of a person's attitude, a main effect of a person's education, and an attitude by education interaction. So let's put numbers to that. The intercept represents 30. The main effect, which I should call the conditional main effect of attitude, is a 1. The conditional main effect of education is a 2. And actually, this is, I believe, parents' education here. The interaction, the two-way interaction of 0.5. So given any values of the predictor variables, the model equation provides predictions for the value of the outcome, right, and any conditional main effects that we plug into it. Right? And so how we figure out what that main effect happens to be, how we figure out what the main, so when we talk about this, the value of 1 represents the main effect of attitude when a parent education is equal to 0. So this is the, describing this, I believe this example, let me go back to this example a little bit more. A person's GPA is influenced by a parent's attitude towards school and a parent's education level. This is a study, a hypothetical study you could have. So parents' attitude towards school, parents' education level, and then the interaction of parents' attitude and education level itself. So this 30 right here represents the predicted value for a person whose parents have 0 attitude. I believe that's on the low end of the scale. 0 education, that would also be on the low end. And GPA in this case would be out of a 100-point scale, 0 to 100. So 30 would represent somewhat of a low GPA in that case. The main effect 1 would represent, would show that for every 1 unit increase in attitude, GPA would go up 1, but that's conditional on a parental education value of 0. And that's because a 0 for education would show up over here in the interaction, knocking this term out of the model, leaving the only part with attitude included right here in the main effect. Similarly, this 2, this main effect, simple main effect or conditional main effect of education, is for a person with an attitude of 0. So for every 1 unit increase in education when attitude is 0, GPA should go up 2. And why that's the case is because when attitude is 0, it also knocks out the other part of the education in the model that would factor into it. So what we can do with this model, though, is not only describe what a predicted value for a person would be, we could talk about how education matters for different levels of attitude, or how attitude matters for different levels of education, which really provides a rich story about what's happening in the analysis itself. So to do that, what we need to do is to figure out how to calculate these simple or conditional main effects. So we have to take out the main effect itself. So this is sort of the rubric, if you will, or the guidepost for how to do this. Take the simple main effect, in this case attitude. Let's say we want to talk about how attitude changes as a function of education, or how the effect of attitude changes as a function of the parental education. We have to take what it is, which is the main effect itself, that's what it is, and we add to it what modifies it. So we take a look at this model equation, we see where the main effect lies, and we see where anywhere else where attitude shows up in the model itself. So attitude's right here, and attitude is right over here. So if we wanted to, so that's step 1, identify all the terms in that. So this part right here are all the terms that modify, that talk about what the effect of attitude happens to be on GPA. And we do a little bit of algebra, and we factor out all the common predictor variable here, right? So here's our term from above. We see that attitude shows up on both sides of this. So we see attitude right here is multiplied by attitude, pull that out, factor that out. It multiplies beta 1 plus beta 3 times education, right there, that quantity right there in the parentheses. So what we're seeing is because the main effect is the number or the constant that multiplies attitude, is that beta 1 plus beta 3 times education provides us the value of the main effect of attitude. So for instance, if education equals 0, we're back to the situation we have when we have the model parameter directly, because beta 3 goes away when it multiplies 0. So if we wanted to calculate this, let's see here. What we can do then is estimate different values of this. So let's try this for a new reference point. If attitude equals 3 and education equals 12. So here we go. Why 0 matters. Y is student achievement. GPA is a percentage grade out of 100. X is parents' attitudes about education measured on a 1 to 5 scale. And Z will be father's education level or parental education level measured in years of education. And here is our model from before. So beta 0 is the expected GPA for a person with 0 attitude and 0 years of education. Beta 1 represents the increase in GPA for a, I notice these numbers are backwards now, but that's okay. Beta 1 represents an increase in GPA per unit attitude for 0 years of education, right here. Beta 2 represents a increase in GPA per year of education for a 0 attitude, and beta 3 represents the either the attitude or the moderator. If we talk about attitude as a moderator, it's the effect of education. It's how the slope of education changes per unit of attitude, or it's how the slope of attitude changes per unit of education. So here, if we talk about plugging in a value of 3 for attitude and 12 for education, we can see that our predicted GPA is 66. So let's take a look at what this happens to me here. Why 0 matters. Let's back this up just a second here. If we go and see our old equation here, what we can do is we can refactor what our new equation happens to be by thinking about, well, let's imagine centering education at, what happens if we center education at 12, right? So let's do that right here. All right? If we center education at 12, we know that we still have to get a predicted value of 66 when we plug in 12 and 3 into what we do, right? So here, education of 12, when we plug that in, what you'll see what shifts is the effect of attitude, right? So when we move the centering point of education, so education of 12 represents a person whose father has graduated from high school. So this is a high school graduate with so now we're saying for a high school graduate, the impact of parental attitude on education, for every 1 extra unit of parental attitude, GPA goes up by 8 percentage points. That's a much larger increase than we saw when education was 0. And that's sort of what's happening with this. Furthermore, what you'll notice is when we center one of the predictors, the effect of the other one changes. And that's because in that interaction variable, the interaction term itself does not change, right? The overall beta weight for the interaction does not change by this, and that's because it's at the top end. It's not conditional on any other value itself. But because attitude's main effect is conditional on the value of education, when we center education, we've changed where 0 happens to be. And because we changed where 0 happens to be, we moved it over by 12. Well, the overall main effect before was 0. We moved it over by 12, so the 12 divided by 2 gives us a difference of 6, which is the new difference between those main effects themselves. So what do you think would happen if we changed, what we think would change if we centered attitudes at 3, but left education at 0 instead? Sure enough, we could probably do this right here. We would have attitude minus 3 right here. Education would be at 12. What we would find here is that our main effect of education would now change. Right? So our main effect of education would move. Our main effect of attitude would stay at 2. Our main effect of education would move because attitude minus 3 shows up right here. And because my attitude minus 3 is multiplied by 0.5, our new effect of education would be 2.5, or another 1.5 units difference from where it is right now. So what we can do with this is to get the model to tell us what we want. And what this is kind of overall doing is telling us that the beta weights tell the entire story of the analysis from start to finish. So if we were to interested in all of what we can talk about is what we know what the main effect happens to be. We can talk about this real quick by parsing out the main effects. Again, remember that rubric of the main effect, or the conditional main effect, is what the value of it happens to be plus what modifies it. So the effect of attitudes is this right here, beta 1 times attitude plus beta 3 times attitude times education. We factor out attitude, and we don't even need to put it up there. We get beta 1 plus beta 3 times education. The effect of education is opposite to that, beta 2 times beta 3, beta 2 plus beta 3 times attitude. And then what we can see is the effect of attitude, or this interaction term, is just 0.05. So now what we can do is use these values to go give us our new 0 points if we really wanted to do so. So here's what we would have. The new equation using centered predictors would give us, oops, right here. You can see it all right up here. Here's our old equation. Our new equation we saw before when we put 12 in for education. The new main effect was 8. Similarly, the same thing about 2.5 as well. So here, where did I get that 12? Beta 1 was 2, the old equation, plus 0.5 times education. Well, if we centered education at 12, we know that beta 1 happens to be 8, right? Because 2 times 1/2, 2 plus 1/2 times education gives us 8. Similarly, if we centered attitude at 3, we'd get 1 plus 1/2 times 3, or 2.5, as we go forward. So, how do we test the significance of this? We need to do this with the GLHT function in the Multicomp package. So again, we can use this forward here. The other thing we could do slowly, I don't particularly recommend doing this, but you could recenter predictors and rerun the LM function. I think that can lead to issues as well. We could also do hand calculations. That's also hard to do unless you go and figure out what it happens to be. But really what we're after is we need we need a new standard error of whatever this main effect or this conditional main effect happens to be. And the way we find that is the standard errors of our previous betas plus the covariance of our previous betas, which doesn't even show up in output. And let's just forget about the hand calculations for now. So here's an example. Let's put this into work with our data that we started with this morning. This morning. At the beginning of this lecture here. And let's talk about putting this in R. So I'm going to load our EPSY905R library, bring out our data test experiment, and save it as a brand new data object. So now you can see it in our environment right here. There's our data. We have a person ID, senior, new, group, and test. And now we're going to load the Multicomp package itself. I'm going to then create factors for my variables. These are objects in R that allow this R to do the coding for us. And I can show us the summary statistics here for each of the groups if you wanted to see this. This talks about that very first table that you saw on slide 3 right there. Let's get into our brand new model 1. This is using their dummy codes instead of factors. So now we're going to say that the test score is equal to senior plus new plus senior times new. And when we look at our summary for that, here we go. What do we find? We find that the overall intercept is 80.2, and that represents the value, the predicted test score value, or the average test score for someone who's not a senior, a freshman, in the old method of instruction. And if you remember looking at our table from slide 3, that was the mean of freshmen in the old method of instruction. So that seems to sync with the data. Now, the effect of senior, this is a conditional main effect because senior and new show up together. And I'll just flip over to the slides here. And what we see with that is that means that the senior group, because it's one, senior is 1, we'd say that the mean difference, because it's a coded group, the difference between seniors and freshmen, now for which class? Is it old or new? Well, because it's in interactions in present, we need to look at the 0 value of the interacting variable. So in that case, it would be for people in the old method of instruction. So the difference between seniors and freshmen in the old method of instruction happens to be 2.16. Similarly, how we interpret the new main effect, conditional main effect, would be this is the difference between people in the new method and old method of instruction for freshmen, because senior is the interacting variable. And finally, this is the difference between senior, or the interaction represents kind of the overall combination describing what happens when seniors and freshmen show up in the same new method of instruction. Now, the analysis of variance table that you see below, what this table gives is a different type of test statistic than you see from the test statistic that comes in the table above. So if we use the ANOVA function in R, if we just run that ANOVA part right here, we see that the senior, that this table, this gives us the marginal effect of being a senior. So this is not looking at the conditional or simple main effect that you see up here. This is just seniors versus freshmen overall, regardless of class they happen to be in. This is the margin of the table that you saw on slide 3. If I go over there, seniors versus freshmen, right here. That's comparing these two means right there. Similarly, the new method, this is comparing new versus old method, regardless of whether you're a senior or a freshman. So if I go back to slide 3, this is looking at this margin of the table right here. And so you'll see the results seem to kind of sync with what we understand, in that there's a big effect of the method of instruction. This is a big F value, small p value. But there's very little effect of being a senior, and there's very little interaction itself. This table is very different than what the table you'd typically see in SPSS or SAS, in that when we go and put in the analysis as this regression effect, when we do the coding ourselves, typically in the other packages, the table that comes about is a conditional table. So where you would typically find the t square equal to f function. If we took the t value and squared it, it'd be equal to the f value below, but R does not do that for us, so that's a nice thing. Now we can go and code up, using the GLHT function, we can go and code up the different means themselves. So here, let's say mean 1 is the mean of freshman old, and again, there's 4 beta coefficients. So I create 4, embed these 4 numbers within this line of syntax, and you can pretty much use this verbatim. 1 for beta 0, 0 for beta 1, 0 for beta 2, and 0 for beta 3 gives us the mean of freshman old. And we do the same thing for each of the combinations that we have. We combine the means together, and when we submit that to GLHT, we see the means of each of the tables. We see their standard error, we see their t-value as well. So that comes from the beta coefficients that you see here, and this table right here gives us all 4 of the betas multiplied by the numbers that we put into the analysis itself. And this gives us the numbers from the table as you saw before. You'll note here the standard error is identical for each of those 4 output, and that's because the model assumes that the variance is homoscedastic. It does not change by group. And you know, in practice, that doesn't seem likely to hold, although this doesn't seem to be a big violation. Later on, when we get to more mixed effects models, we can actually estimate a separate variance by group as we go forward, but not right now. So what if we wanted to talk about mean differences between each of these, or we want to talk about, with the model implied main effects themselves? If we wanted to talk about the effect of senior, right? What's the difference between seniors and freshmen? For the old method of teaching, it'd be beta 1 itself, because that's part of the coding system. The effect of seniors in the new method of teaching would be beta 1 plus 1 times beta 3, and so we could code that right here in effect 2. We could talk about the new method of effect. We could talk about the difference between the old and new method of teaching for freshmen. That would be beta 2 by itself. And the new method for seniors, so the difference between old and new for seniors would be beta 2 plus beta 3. So we see up here, this one. So we code those up in GLHT, we add them together, and we see the effects. And now we can see that the new method has a significant effect for both freshmen and seniors. And then if we're going to look at the senior effect, the seniors had a slightly significant, or a mean difference of 2.6, which was roughly significant. It's smallish p-value depending on your alpha level. Let's call it significant. There was a significant difference between seniors when we used and freshmen in the old method of teaching, whereas in the new method of teaching there was no significant difference. So this is a nice way of looking at our effects a little bit more thoroughly in an analysis. And what we basically see from this output is that we get each of the betas represents something in this table overall. So beta 0 represents the reference group. Beta 1 is the difference between the reference group and this kind of senior column. Beta 2 is the difference between this reference group and this column. And beta 3 is kind of what needs to be added to put it all together. And we could go and get the means for the others moving forward as well. Now, if we use factors in R, nothing changes. It's one of the nice things about R, whereas if we were to go in, for instance, in SAS, there's something called a class statement. If we change that, then all the output starts to change a lot, and that causes a little bit more confusion. I will say the one thing about R is when you use a factor, it codes it for you, and you have to figure out what that means, what the value of the reference group happens to be, and that's one of the harder parts to do. So, to summarize, there's these two types of main effects. There's conditional and marginal. The conditional main effect p-values are conditional on the interacting variables. Their summary function gives you the kind of the p-values for each of those. And the marginal main effects are unconditional on the interacting variables, and those show up in the ANOVA function. So to summarize, the purpose of today's lecture was to drill into what interactions happen to be. This is a very complicated topic. This lecture is not going nearly enough time on it, but the upcoming in-class portion will drill more, and the first homework in class will give you much more practice on this as well. Not only that, but interactions are going to show up in examples throughout class this year because interactions are such a critically important topic. You find them show up, and particularly if you go into longitudinal analysis or multi-level models, you will find interactions almost from the start in any analysis that you get into. So it really is important, and that's why I show this in this lecture today. So this is not SAS versus SPSS. This is R for linear models. And what we're going to say here is we can work with R. This kind of gives us a scorecard as to how to get R to give us what we want in our analysis. So using the LM function, we can tell it the dependent variable before the tilde. If we just enter the variables in afterwards and we know that they are not categorical, then they show up as continuous predictors. If we know that they say factor, then we know they are categorical predictors, and R will code them for us. If we want to go get the fixed effects, or to give us means per group, or to give us model implied effects, we use this GLHT from the Multicomp package. And if we want to see the solution for things, we can do the summary or ANOVA statement. So I hope this has at least been an introduction to it. I know things are going to be up in the air, but as soon as you get some hands-on practice, hopefully it'll make a little bit more sense. Okay, that's all for now. Thank you.